So in order to understand this, we have to go to Fourier and Laplace transforms. These two will help you understand what I'm talking about, okay? So first, I will start with Fourier. Fourier has two parts, one which is called the Fourier series and one which is called Fourier transform. Fourier series is used for what? It is used to convert any signal or any periodic, specifically any periodic signal, into a DC component plus a group of sine and cosine. So Fourier series, this representing a periodic function, takes a periodic function as a sum of sinusoidal functions of different frequencies and plus a DC component. This one is used to analyze and represent periodic signals in terms of their harmonic components. So this is how you can convert any signal into a Fourier series. Now you can see that it is consisting of any function of t using Fourier series can be analyzed into a node over 2, which is called the DC component, plus summation of cosine and summation of sine signals. These cosine and sine, you can see that they have 2 by nt or omega nt, where n is from 1 to infinity. What does it even mean? So we have cosine omega t, we have cosine 2 omega t, cosine 3 omega t, and infinity. Okay, similarly for sine signals. Okay, so in the end, any periodic signal can be converted into a DC component and the group of cosine and sine. Now this is very important in many applications, including the power system analysis, or specifically when we are designing harmonic filters. So due to the presence of non-linear loads in electrical systems, we will have harmonics, which can cause many problems in electrical systems, including overloading of transmission lines, including increasing of losses in transmission lines, can lead to distortion of voltages, many problems we have. So in order to design a filter that will eliminate these harmonics, we have to know what harmonics are even presented in our signal. So by knowing what harmonics are presented and their magnitude, by using Fourier series, we will be able to design a filter that kills the dominant harmonic. Okay, that is the whole purpose of Fourier series as one of the applications in electrical systems. Okay, now for Fourier transform, this is similar as Fourier series. However, it is used for non-periodic functions and signals. So it is a special case of Fourier series. Okay, so Fourier series for periodic functions, Fourier transform for non-periodic functions, which does not repeat itself. Now it is used also to take a function and decompose it into frequencies to see how much of each frequency is present in the original signal. Now you will ask me, why do we need Fourier transform? So we now understand Fourier series convert any signal into sine, cosine, and DC component so that we can design a filter. Now Fourier transform is similar to it, but it can be used for non-periodic functions, which does not repeat over time. So this is Fourier series, a function composed into sine, cosine, and a DC component. For Fourier transform, the function becomes a function in omega, or the angular frequency. Okay, so we convert it from the time domain to a frequency domain. So we say that Fourier transform convert a signal from the time domain to frequency domain, or j omega. So the equation for Fourier transform, we put our function here and multiplied by e to the power negative I omega t or j omega t. I here is the complex number, okay, imaginary number I, which is root negative 1, okay. So when we add our function here, we can get the output, which will give us the signal as a function of omega, which will help understand where our signal exists in the frequency domain. Now let's see some examples for this to understand the idea. So for a Fourier series, we said that it is used for periodic signals, right? We used it for periodic signals. Now for periodic signals, we have like this. We have this one, which is a periodic signal, repeats itself, okay? Now by using Fourier series, we can analyze this signal into a DC component plus group of sine and cosine. There are special cases where we don't have sine and another case where we don't have cosine in even and odd functions. Okay, it doesn't matter right now. All what is matter is that we understand this concept. So you'll find that this one consists of a DC component that pushes it up. This is a DC component, okay? So this is our original signal and this is a DC component presented in it. Now let's say that we found the first component at omega naught 1 omega naught fundamental frequency. So we found that using Fourier series having this shape. Now let's take this and add this. So we have a DC plus fundamental component. So we will have this signal, okay? Now let's say we found the second frequency component, double omega. You'll find it is like this using Fourier series. Now add these three together, you will get this shape here, you can see becoming closer and closer to our final shape. Now let's say we found the triple harmonic. It is like this. So if I added all of this, we will have this shape. Now fourth component, or four times the fundamental frequency. So it will become closer and closer like this. You can see it became close to the signal. Now if you get the fifth component, 6, 7, 8, 9th, and etc., you keep adding it until infinity, you will be very, very close to this rectangular shape. Okay, that is what Fourier series do. It tells you, hey, what is the DC component we have, and plus what cosines and their amplitude, and what cosine and their amplitude. Okay, now for Fourier transform, what does it do? It looks at a signal like this. This is a signal in time domain. This signal is non-periodic signal. It doesn't repeat itself. Okay, now we take this signal and decompose it into group of sine. You can see one sine, another sine with double of frequency or triple the frequency, and another sine with another frequency. Now by analyzing this, you will find that this wave, for example, it's consisting of 1, 2, 3, consisting of 3 signals. Each of these signals has a certain frequency and certain amplitude. So when we plot this in the frequency domain using Fourier transform for non-periodic, again non-periodic, it will be like this. It will be this frequency omega 1, this frequency omega 2, this frequency omega 3, and the corresponding amplitude A1 amplitude of the signal, A2 amplitude of this signal, and A3 amplitude of this signal. Now for Fourier transform, again as we said before, the time domain gives us signal changes over time, and the frequency representing how much of the signal exists within a given frequency band concerning a range of frequencies. So it converted it into a frequency domain, and by doing so we can decompose it into sinusoidal components with frequency, amplitude, and phase, similar to Fourier series but for non-periodic signal. Now you will say that why do we even do this? Why do we use Fourier transform for non-periodic signal? So exactly as we did before, you can see we transformed a signal like this into frequency domain using a Fourier transform. You can see using Fourier transform or Fourier series. Fourier transform if it is non-periodic, Fourier series if it is periodic. Like this here, you can see it has a certain amplitude and frequency, 1 kilohertz, frequency, amplitude, frequency, and amplitude. Okay, now I need an application for this, for the frequency domain or Fourier transform. So you'll see that, let's say I have a recording like this, okay, which is non-periodic, giving this output signal. Okay, now what I would like to do is that I would like to delete or remove noise, right? I would like to remove noise from this recording here. So how can I do this? So I need to know the noise frequency and design a filter to remove this noise. Okay, so what do we do is that we take this function here and take it to like this, x as a function of t, or the recording here, we put it in the Fourier transform for non-periodic signals, and it will give us x as a function of omega, or the amplitude and frequency, amplitude and frequency, amplitude and frequency for different frequencies. Okay, so by using Fourier transform, we obtained amplitude and the frequency presented in this non-periodic signal. Now you will see that the noise have a very large frequency, as you can see here, with a large amplitude. This one is our noise presented in the recording. So what I'm going to do, I will look what is the frequency of this signal, and then I'm going to design a filter that kills this particular frequency from this audio. So by taking this signal into a filter, by taking this frequency domain signal and getting it to a filter, you'll see some of the signals will be killed, right? You can see this one died here because this filter will not affect this one only, but it will affect other signals. But this filter will strongly, this is a low pass filter that will pass small frequencies and kill high frequencies. That's why these frequencies are passed normally. However, high frequencies like here, you will see that they are almost dead due to the effect of a low pass filter. Okay, so we will have this signal. Then I'm going to use inverse Fourier transform to convert from frequency domain into the time domain again. Okay, so this is our recording without any kind of noise. This is useful. This Fourier transform is useful in one of these applications. So we have seen Fourier series for harmonics, Fourier transform for like music or audio or anything like this.